Hello and welcome to this film, which is all about explaining some of the trends that we see in the periodic table. Now hopefully in previous films you've learned about what we mean by the electronegativity of an atom, its atomic radius and its ionization energy. Here we're going to have a look at explaining how these things vary in the groups and periods of the periodic table. We're going to try and do that always by using these three factors of nuclear charge, that is to say the number of protons in an atom, because remember the charge of a nucleus comes only from protons, because neutrons have no charge, the amount of shielding in an atom. Now shielding is something that the inner shell electrons do to the outer shell electrons. If I'm an outer shell electron and there are electrons in shells within my shell, so that is inner shells, then those inner shell electrons will shield me from the nuclear charge. Okay, so for example, if I was an outer shell electron in an atom with 11 protons and there were 10 inner shell electrons inside my shell, then I would effectively only see one proton. Okay, and then finally the number of shells, which, as we know, the more shells you have in an atom, the further and further the shells are getting from the nucleus. So let's have a look first of all how these three factors are going to affect atomic radius. Okay, we'll start off by looking at what happens as we go from left to right in the periodic table, that is to say across a period. Okay, now what atoms have we got here? Well, we've got sodium, oops, what's going on? My pen isn't working. So there's sodium, element number 11, okay, in group 1. And this here is element number 12, that is magnesium, okay. Now, we should by now be able to look at the periodic table and decide on the electron configurations of these two atoms. Okay, so we won't talk about that too much, but let's have a think about how these three factors have changed as we move across this period from sodium to magnesium. What's happened to the nuclear charge? Well, it's gone up by one proton. Okay, so the electrons are feeling more of an attraction from the nucleus. What's happened to the shielding? Now remember, we're only really considering the outer shell when we're talking about the atomic radius, because it's the distance from the centre to the outside of this notional circle. Okay, what's happened to the amount of shielding? Remember, shielding is provided by inner shell electrons. Now sodium's got one outer shell electron, magnesium's got two, but they've got the same amount of inner shell electrons. So this nuclear charge has gone up by one, the shielding hasn't changed, okay? So essentially these outer shell electrons are seeing more charge in magnesium than they are in sodium. What's happened to the number of shells? That stayed the same. So overall, there is a greater attraction to the nucleus in magnesium than there is in sodium. That means that all these electrons are going to get pulled inward towards the nucleus, and that means that across a period, the atomic radius is going to be falling. Okay? Now, what happens to these three factors if we go from sodium to potassium? I'm going to do this in red. Okay, so we're going down the group now. I'm going to do it in red so that I don't have to rub everything out. Okay, what's happened to the nuclear charge? Well, it's gone up. Okay, sodium has got an atomic number of 11. Potassium's got an atomic number of 19. So potassium has 8 more protons than sodium. What's happened to the shielding? Well, there's 8 more inner shell electrons in potassium than there are in sodium. So in spite of the fact that the nuclear charge went up, the shielding went up with it. In fact, it went up just as much. So these two basically cancel out. Okay? What's happened to the number of shells? Well, that's gone up. So now we can see that as we're going down a group, it's a little bit harder to explain now because we've got to bring in this fact that the shielding is cancelling out the nuclear charge. These two things cancel out. We're left with just this remaining factor of number of shells, so as we go down a group, the atomic radius should be increasing. Okay? So I suppose at the heart of this, we've just got to make sure that we remember that across a period, the atomic radius goes down, and down a group, it goes up. But we've also got to be able to explain that in terms of these three factors. Okay, moving on to electronegativity and something called electron affinity. Now, electron affinity is rather like electronegativity. Electron affinity is just basically how much energy is released when an atom gains an electron. Okay, you're going to release more energy when you gain an electron if you really like holding on to electrons. Okay, so these two things are kind of linked, but we didn't cover electron affinity in the previous film, so it's just worth mentioning that the electron affinity is a measure of the amount of energy released when an atom gains an electron. Well, let's think about what would happen, what would cause an atom to attract electrons strongly. Well, if there was a high nuclear charge, you'd think the electrons would be attracted strongly. If there was a lot of shielding, you might think that would cancel some of that nuclear charge. If there was a lot of shells, then the distance from the nucleus would be greater, and so the attraction might fall. Okay, so let's have a think about what's happening as we go down a group in the periodic table and as we go across a period. Now, often it's useful to remember that the most electronegative element is fluorine. Okay, fluorine is the most electronegative element. You find it in the top right of the periodic table. So we can see that immediately electronegativity is increasing as we go from left to right, and it must be falling as we go from top to bottom if fluorine is at the top right and it's the most electronegative. Also tells us that francium should have the lowest electronegativity because it's all the way over on the left and at the bottom. Let's see if we can explain that. Okay, we'll start off by talking about this trend here, so across a period. What's happening to the nuclear charge? Well, as we've seen before, that's going up by 1 each time. What's happening to the shielding as we go from one atom to the next? Nothing changes. What's happening to the number of shells? Well, they've all got the same number of shells. So those two things are staying the same. Nuclear charge is increasing. That's allowing us to explain why the attraction for electrons is getting higher as we go across a period. So the electronegativity is increasing. That's a really horrible looking arrow, but I'm going to leave it there because otherwise I've got to rub everything out. And electronegativity and electron affinity are both increasing as we go across a period. What's happening to these three factors as we go down a group in the periodic table from top to bottom? What's happening to the nuclear charge? Well, that's going up, as we've seen before. What's happening to shielding? Well, that's going up along with it, and it's going to cancel it out. These two things cancel, remember. Okay? If the number of inner shell electrons is increased by the same amount as the number of protons, then these two things cancel. What's happening to the number of shells? That's increasing. What's happening to the attraction of the electrons to the nucleus? Well, if these two things have cancelled, then all that we're left is this increasing distance from the nucleus. Then the electronegativity, the strength of the attraction, must be falling as we go down the group. So that's how we explain that. Now, finally, let's move on to the first ionisation energy of an atom. This, remember, is the amount of energy we have to put in to remove an electron. Now, you might think if an atom is highly electronegative, it holds onto its electrons very strongly, then we'd have to put in a lot of energy to remove an electron, and you'd be quite right. In fact, if you look at this graph, every time we go across a period from hydrogen to helium, it's increasing. Now we drop down a period to the next period. So now lithium is in group 1 beneath hydrogen. It's got a lower ionisation energy than hydrogen, so we're going down the group, it's falling. Now we're going across the second period, and there's this general rise. We don't have to worry about these little blips that you see, okay? Now we move across to sodium. Sodium is in group 1 below lithium, so it's got a lower electronegativity and a lower ionisation energy, and then again across this third period they're gradually rising, and so on and so forth. Again, let's see if we can explain this in terms of our three factors. Well, what's happening as we're going across a group, across a period from left to right? The nuclear charge, as we've seen before, is increasing, the shielding is staying the same, the number of shells isn't changing, so this is the only factor that we're really concerned with. If the nuclear charge increases, stronger attractions, harder to remove electrons, more energy needs to be put in. So as we go across a period, there's this upward trend of ionisation energies. Okay, as we go down the group, so from top to bottom in the periodic table, what's happening? Oh, I should have done that in a different colour, I suppose. So here's the red one. And what's happening to these things? Well, just as before, the nuclear charge is going up, but shielding's going up with it, and these two cancel. So effectively, they're not part of our considerations, but that doesn't mean we shouldn't mention them. Okay, the number of shells is increasing. The further the electrons get from the nucleus, the weaker the attraction will be, the less energy we'll have to put in as we go down the group. So ionisation energy falls down any group of the periodic table. Okay, so hopefully you feel like you not only know what the patterns are in electronegativity, atomic radius and ionisation energy, and also electron affinity, but also that you can explain them. And hopefully you also know the importance of trying to mention each and every one of these three factors in your explanations. Hopefully it makes sense. If you've got any questions or comments, please feel free to come and see me or to post a comment on YouTube.